has been recorded. Okay, will be recorded. Okay, so let me start with the lecture of momentum. All right. So what do you still remember about the last class? What did we learn of the last class? Anyone?
Deflectors.
Pardon? Deflector. So how
Deflectors.
many deflector? Okay, the last class, what type of deflector that we learned? Okay, just a recap. The last class we learned about deflector. Alright, for this we need to talk more on. I need to talk more on the deflector, propeller, and dimensional analysis. Alright. So for the newcomer, we have three students for joining the session. Okay, my name is Muhammad Nur Hidayat. Okay, I'll be your instructor for this fluid mechanic SEMM 2313. Okay. Alright, the last class we learned about deflector. So what is the deflector? The deflector is actually used to deflect the fluid to the blade. Alright, in order to extract the energy coming from the nozzle. Okay, this is the impulse turbine. Do you know the function of impulse turbine? To extract the fluid energy and then convert it into the kinetic energy. Alright, so this is the kinetic energy, the motions of the turbine that will produce the power. Okay, so from this position, this point 1 to point 2, we have the momentum. Alright, so this momentum, we apply the momentum equation. Okay. And the last class, we learned about the stationary deflector. That means this deflector, you can see here. Alright, this deflector is full stationary with the reaction force acting in the X and Y direction. Okay, this is the impact jet, alright, or nozzle. The nozzle give out the fluids and then impact the deflector in this direction. So we know that deflector is a function to deflect the fluid from this point 1 to point 2. It deflects at certain angle. We call it as the alpha. Okay. So based on the momentum equation, by applying the Reynolds transport theorem, this is the momentum. Remember that momentum is mass multiplied with velocity. Mass multiplied with velocity. Okay. So mass multiplied with velocity divided with time. This is the change of momentum. The change of momentum is what we call the force. Alright. So F equal to ma, where the ma is the change of momentum. You look at here, velocity divided with time is acceleration. Mass multiplied with acceleration is the force. Okay. By applying the Reynolds transport theorem, that consider two components, which is the first part is the control volume that directly depends on the time, and second one is the control surface. Okay, this is the flux. This refer to the flux term. This refer to the change of control volume. Okay, since we consider this as the steady state, that means the change of time equal to 0. So the summation of force will equal to this component. Okay, equal to the control surface component. And then we apply the, okay, one inlet and one outlet at the control surface. You look at here, this is inlet, this is outlet. Okay, we derive at the final conclusion, which is M dot equal to V2 minus V1. How it comes from this one? Can you see? Okay. M dot refer to rho VA. Okay, rho VA is the M dot. And V here refer to the change of velocity. That is why V2 minus V1. Okay, so from here we know that the force is the vector quantity. That means it has magnitude and direction. The one that we are talking here is the magnitude. So in order to get the direction, we need to separate into two components, which is x and y component. That is why the summation of force going to have fx and fy. So we find the summation of force in the x component, it will be negative rx. Okay, and this one mv2 minus v1, this is what we call a simplification from v2. Okay, v2 we know already. V2 is, in order to get v2 in x component, v2 cos alpha. Can you see? v2 cos alpha. Okay, for y component, in the inlet we don't have y component. That is why V2 only. Okay, we know that V1 equal to V2 according to the continuity equation, because we have the same cross-sectional area at the inlet and the outlet. That is why V2 we replace with V1. Okay, what if V1? V1 is the velocity inlet coming from the nozzle jet. Okay, so far you guys have any question pertaining to this, the last chapter?
Not for now, Doctor.
Okay, because, okay, thank you. Because the last class, I already explained about the stationary deflector. Okay, for that part, I just want to do the revision so that you can remember. Okay. So now let's talk about moving deflector. Okay, this is what we learned the last class. We derive until we come up with this equation. Okay. Okay, this lecture note has been uploaded in the e-learning. You can access it, okay, to fill up on your own. Okay, for now, we talk about moving deflector. Okay, the last class, the last week, I explained to you about the stationary deflector. Now we have a moving deflector. So what's the example of moving deflector? You can see here, we have the snowplow blade, all right? This is considered as the moving deflector. Why? Because this blade is act as the moving deflector, moved by this tractor, all right? So the function of this snowplow blade to clean the roads due to the snow, all right? So for this case, we consider as the moving deflector. So moving deflector can be either single moving deflector, this is single, okay, or a series of moving deflector. Okay, you can see here, we have the turbine. Okay, so where is the turbine located? Okay, can you silence, Ibrahim. I think Ibrahim. Okay, thank you, Ibrahim. So, this is we call a series of turbine. Why we call a series? Because it is more than one deflector. Okay, you look at here, this turbine have so many of the deflector. We call as a series because it is arranged in a series. This is the first phase, second phase, third phase. You can see here. Okay, we have so many number of phases, right? So in the turbine, normally we have two components. All right, the impulse turbine and reaction turbine. Okay, so what are those? Okay, let's take a look of this. Okay, this video. Okay. Okay, can you hear?
No.
No, doctor.
No.
Okay, cannot hear. Let me explain. Okay. So this is the impulse turbine. So can you see the name mentioned impulse? That means it is impact. All right, from one position to another, we call impulse. Okay, it is impact from this nozzle impact to this bucket. All right. So initially the bucket will rotate due to the impact of the nozzle, the water coming from the nozzle. This is solely depend on the velocity. The velocity of the nozzle impact this bucket that will turn the bucket anti-clockwise. So this bucket will attach to the rotor. And then once the rotor rotate, it will generate the electricity or power. Okay, this rotor is actually the shaft connecting to the generator. Okay, this is the impulse. Okay, may I ask you, what is the function of nozzle? Anyone? What is the function of nozzle here?
Increases velocity.
Yes, perfect. Absolutely. To increase the velocity, if you have the increase in velocity, what will happen? High velocity will increase the what kind of energy?
Electrical energy.
Pardon?
Electrical energy.
Before electrical energy.
Oh, rotational mechanical.
Okay. Before the mechanical.
Kinetic.
Yes. Kinetic energy. So what's the formula of kinetic energy? Half mv squared. So you can see we have the velocity. Higher velocity will increase the kinetic energy. So the kinetic energy will impact this bucket will rotate. So that is the impulse turbine. Okay. So how about the reaction turbine? Okay, this is the example of reaction turbine. Okay, this is the Francis turbine. Can you see? Okay, the how it works. Anyone knows how the reaction turbine works? Anyone? Anyone knows how the reaction turbine works? Okay. Okay. Let me explain here. Okay. So, you look at here, this is impulse. Remember that the impulse is solely depend on the impact or the velocity from the nozzle. Okay. This is what we call as the impulse. It depends on the velocity. However, for the reaction turbine, it depends on two things, the pressure and velocity. That can be directly related to Bernoulli. Okay, so what Bernoulli said about high pressure? High pressure relates
Low
to
velocity.
low velocity. Low pressure?
High velocity.
Yes, high velocity. Okay. So, in here, do you still remember the Bernoulli equation? P over gamma plus V squared over 2G plus Z
Z1.
equal to constant. Okay. So let's move this term, these two terms, second and third term to the other side. So P over gamma equal to constant minus V squared over 2G minus Z. Okay, let's focus on this term only. Okay, so we have the P component and we have the combination of these. So increasing the P, okay, I explain you increase the P. Why the velocity reduce? Okay, let's say I increase this term, the P. So what happened to the velocity? The velocity has to decrease. Can you see? Because it is minus. If the velocity increase, what's the value of C? It will decrease. Remember? Okay. So increasing the P will reduce the velocity. Because the velocity need to minus with C. Can you see C minus velocity? Anyone? Do you got it? From the Bernoulli equation?
Yes, doctor.
Okay, so P has to increase and the velocity has to decrease in order to maintain the to increase the C. Okay, so that is why we come up with this term. Okay, and then we realize that okay, this is aerofoil. Okay, this is the flow. Okay, this is the velocity streamline. Okay, what do you think of the velocity at the bottom? VB. And this is velocity at the top. Is it, which one is higher?
VB is higher.
Okay, VB is higher. And VT?
Lower.
Okay. So, okay, why because of higher? You can see here, the flow is streaming without any obstacle, right? That is why the velocity at the bottom higher. You can see here. Once the velocity reach here, this is the obstacle. Can you see? This is the obstacle, right? This is the obstacle. And then it will reduce. It will have the drag. dragging, and reduce the velocity. In turn, lower velocity will, okay, sorry. Okay, okay. So from here, okay, sorry. Basically, it is not the velocity here. Okay, let me repeat again. Okay, like this. This is the distance. Okay, which have the higher distance, longer distance, the top or the bottom? The distance, everyone. Which has the longest distance, the top or the bottom?
The top.
Okay,
The
the
top.
top will have the longer distance. Okay, because you can see the curve, right? So this fluid particle, okay, will reach at the same time. Okay, this is the end point. Okay, so this has the longest distance, but both of these fluid particles need to reach this end at the same time. So which one will have the highest speed? Okay, this is, for example, this is Ali. This is Abu. Okay, the Abu has the shortest distance, but the Ali has the longest distance. But the rule is Ali and Abu need to arrive at the same time. So which one need to run faster? Ali or Abu?
Abu.
I think Ali.
Okay, why Abu need to run faster? Okay, you can see Ali has the longest distance and Abu has the shortest distance. At the end of the time, Ali and Abu has to arrive at the same time. Okay, which one Ali or Abu need to run faster?
Ali.
Ali.
Okay.
Ali.
Definitely Ali, right? Ali need to run faster in order to catch up with Abu. Right. Okay. So that is why the velocity here, the velocity at the top is a little bit higher than the velocity at the bottom. Okay, because of this analogy. Okay, so because of this higher velocity, it will turn to be lower pressure. Can you see? Higher velocity, low pressure. This is low velocity, higher pressure. So this pressure will push this upward. Okay, do you think this is lift? It will lift or not? This aerofoil, definitely it will lift the aerofoil because of the pressure difference. The pressure at the top is low compared at the bottom, so it will lift the aerofoil. That is why the aeroplane can lift. Okay, so same goes here. Okay, you look at here. This is the reaction turbine. Okay, this is the vane. We call it as a guide vane that will guide the fluid particle. Okay, this is the blade. Okay, initially this is very high pressure. Okay, this is very high pressure. Pressure is very high at this point. Okay, this fluid particle will have very high pressure. In turn, it will have low velocity, right? Okay, based on Bernoulli principle. So because of the change in the cross-sectional area, okay, it will turn the pressure to be low, pressure low, and the velocity high. Okay, because of the cross-sectional area change here. That is why the velocity upon the guided upon the outlet have the highest velocity. It will give the momentum. Okay, so that is why the reaction turbine depend on pressure and velocity. Impulse turbine depends on velocity 100%. Okay, so far do you have any question pertaining to the impulse and reaction turbine?
No, doctor.
No, doctor.
Alright, for a single deflector, as I mentioned before, this is the single deflector. Alright, like a snow blade here. It is a single deflector moving in the positive x direction. Okay, for this case, let's consider this analysis. Okay, you look at here, this is the single deflector. Okay, and this deflector have the reaction force. Even it is moving, but we consider it is something that hold the deflector. Okay, otherwise it will fall down. Let's say it is hold the deflector before the impact. Okay, so this deflector, this moving deflector have the reaction force. We call as the R component. Okay, and then this deflector, when we consider the reference frame, you can see here, this reference frame is actually attached to the deflector. So what is the reference frame? It is a X and Y component. When we talk about the reference frame, it is the X and Y component. This is our frame. Okay. So where is our X and Y? You can see here. This is Y and this is X. Okay. So why we need to consider this as our reference frame? Because we need to make sure it is a steady flow. When we consider this as our reference frame, it will cause this unsteady flow because there is a relative motion from this point to this point. Okay, so we need to depend solely on this imaginary line as our reference frame. Okay, so right, let me check first. Hence, the momentum equation become right. Okay, let me write this down. Okay, so the momentum equation, we know already that the summation of force previously is mass flow rate V2 minus V1. This is the general part. Okay, so when we consider it is X and Y, we need to separate into V2X minus V1X. Okay, and this is also the same, V2Y minus V1Y. Okay. So from here, let's say the summation of force. Okay, summation of force in the X component is equal to mass flow rate multiply with V2X minus V1X. Okay, so for this mass flow rate, we consider the mass flow rate. Okay, okay, for this case, okay, let's take a look of V2X. Okay, let me zoom. Okay, this is the inlet and this is the outlet. Okay, V2X. Okay, before I explain V2X, I need you to understand that Okay, the velocity coming from the nozzle is V1. Okay, the velocity inlet from this boundary condition is VR1. Okay, this is VR1. That means velocity relative to 0.1. You can see VR1, velocity relative to 0.1. And here is the velocity relative to 0.2. You can see VR2. So, VR2, we perform the triangle vector. This is VR2. And then this moving deflector move at velocity VB. You can see VB. So VB is moving horizontally. So that is why it is VB. VR2 and VB is V2, which is here. So now we know the magnitude and the direction of V2. So same goes here. The velocity from the nozzle here, this is nozzle, is V1. From here, from this outlet to this here, this is V1. And then this is VR1, velocity from here to here. Okay, the velocity inlet of this boundary. And we represent here. And VB is the moving of this deflector. This is deflector moving to the right. Okay, combining VB and VR1, we got the V1. That is why VR1, in order to get VR1, V1, you can see V1 minus VB. Okay, in order to get VR2, you can see, in order to get VR2, V2 minus V1. Okay, however, we know that V1 is actually equal to V2 because of continuity equation. Remember that the continuity equation Q1 equal to Q2, which is area 1 V1 equal to area 2 V2. Do you see we have the same cross-sectional area from this point to this point? Okay, the same cross-sectional area we cancel. That is why V1 equal to V2. Okay, that is why initially it is VR2 equal to V2 minus VB. Okay, we know already V2 is equal to V1. That is why VR2 equal to V1 minus VB. Okay, so from here, mass flow rate. Okay, mass flow rate here, V2x. Where is the V2x? You look at here. We have V2x. Okay, V2x from this boundary. V2x refer to VR2. Okay, VR2. Okay, this VR2 has the angle alpha, cos alpha. Okay, this angle. This is alpha, the same angle with this. Minus V1x. V1x is VR1. Okay. So from here, mass flow rate. Okay. VR2. Just replace here with VR2. You look at here. VR2 is V2 minus V1 or V1 minus V2. Okay, just replace here. So, V1 minus VB cos alpha. This is bracket. Okay, bracket minus VR1. VR1 is VB, V1 minus VB. Okay, from here, remember that now we are considering the boundary condition. So the mass is actually entering this inlet and outlet here is actually relative mass. That is why we need to put the MR, relative mass. Okay, so mass flow rate relative is actually, you can see that this V1 minus VB, V1 minus VB, we can do the factorization. Okay. That is why the final equation become this. Okay, can you see? This is the MR V1 minus VB cos alpha. How about the summation of force in the Y component? This is X component. Okay, so it is the same. Again, summation of force. Okay, summation of force in Y component equal to mass flow rate. This is relative mass flow rate. V2Y minus V1Y. Okay, so mass flow rate relative is the same. So V2Y. Okay, we look at here V2Y, which is VR2 sine alpha. Okay, so V2Y VR2 sine alpha. Now we are considering the reference frame. Remember our reference frame here is actually here. Okay, so anything we refer to reference frame. That is why we use the relative. Okay, so V2Y is actually VR2. Velocity outlet relative to point 2. VR2. So VR2 is this direction. In order to get VR2Y, we have to do VR2 sine alpha. We got the vertical component. That is why here. So minus V1Y. Do we have the velocity in the velocity Y in the do we have the velocity 1 at Y component? Anyone? This component refers to only X. Do we have the Y component, the velocity relative 1 at Y component? No, right? Because you can see here the direction is horizontal, 100%. There is no Y component. There is no slanting. That is why this is referred to X component. For VR1, Y is equal to 0. Okay, so equal to 0 directly. Okay, so mass flow rate VR2. VR2, where's the VR2? How to get VR2? VR2 is equal to V1 minus VB. Okay, V1 minus VB sine alpha. Okay, so therefore that is the final term. Okay, but you notice that this force, we have the negative Rx. So what is the net force in the X component? Can we see? We have the reaction force lengthening. So definitely we're gonna have the reaction force in Ry and Rx. Rx is pointing to the left. It is negative. That is why here it is negative Rx. It is the same here. How about the Y? It is pointing upward. It is positive.
Positive, yes.
That is why positive Ry. Okay. That is the final equation for the moving deflector. Okay, remember this is only the single moving deflector. Okay. Here we have the last, just now I talked about the relative velocity. How about the relative of mass flow rate? Okay, where m dot r is the mass flux exiting the fixed jet with the change of momentum. Okay, so from here we know already what is the formula for mass flow rate, which is rho a v. When this is r, this is r. Okay, so this is the mass flux is actually mass flow rate, yeah. Exiting the jet. So definitely it is a VR1. You can see this is the jet. Okay, exiting the jet is a VR1 coming here. Okay. So from here, rho of the water, yeah, area multiply with VR1 is actually V1 minus VB. That is the equation to find the mass flow rate. Okay, how about the cascade of vane? Okay, the one that, just now I talked about the single deflector. How about we have a series of deflector? We have so many deflector. So let's consider we have so many of deflector. You can see this deflector, 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 deflector. So another name of deflector we can say as a vane. Okay, this is a vane. You can see we have vane 1, vane 2, vane 3, vane 4, and vane 5, and so on. Okay, so in the vane, this is moving. You can see this vane is moving from the left to the right. Just imagine that this is moving at the velocity VB. And what caused the vane move? Because of the jet coming from the nozzle. You can see the fixed jet at the angle of beta 1. And you can see this is the inlet. This is the inlet position. And this is the outlet position. You can see at this is a V1 and this is a V2. Because of the time average position of jet, of exiting jet, this velocity has changed. Okay, just imagine that the first impact of water in this direction. Okay, this is the water impact this. Due to the impact of this water jet, this vane moving from the left to the right. Moving horizontally. Okay, at velocity v. So, the water here, the water outlet will have this direction. Okay, even though we know that the fluid will flow in this direction, right? Because of this profile, this shape. But due to the time average, okay, combination of the moving vane with the moving of this fluid, it turns out that the final velocity will be in this position. Okay, so due to this position, okay, let's we show you the concept. Okay, this is the V1. Okay, let's talk about this is inlet. Inlet position. Okay, this is the V1, yeah. This is V1. Let's say this is V. Okay, this is V1. I think this. Okay, this is V1. And then, okay, entering. Okay, let's say it is entering this one lah. Okay, entering this. This is VR1. Okay, so VR1 is position this way. VR1. Because velocity, okay, let me show you. Okay, let's say this is velocity relative entering this position. This is VR1 and this is VR2. Okay, and this is VB. Okay, now let's make it longer. You can see this is VR1. Let's say this is VR1. So VB is from here to here. This is VB. Can you see the triangle? The polygon of the vector, the polygon of vector, the triangle of vector that show the magnitude and the direction of V1. Okay, this is the velocity from the jet. This is the velocity from the vane. This is the velocity from the boundary condition. Okay, like this. Velocity from here. Let me draw for you. Okay, this is our boundary condition. Okay. So this is inlet. How about the outlet? Okay, where is the, okay, this is the V2, VR2 in this position. This is VR2. Can you see? This is VR2. And how about the VB? This is VB. Where is the resultant force? V2, which is definitely, we can connect this point and we can connect this point. So this intersection is the resultant vector. Okay, so we need to draw V from here to here. This is what we call as a V2. Can you see V2 is the same direction here? Okay, so far you guys have any question pertaining to the triangle of vector?
No, doctor.
Okay, if you have, please let me know. Yeah. Okay, this is the triangle. If all the mass exiting the jet has changed the momentum, okay, we can finally show negative Rx equal to mass flow rate V2x minus V1x. This is the general, yeah, as I mentioned to you, because the summation of force M V2 minus V1. Okay, you can see that X component of force is related to the power output. This moving vane does the do the moving vanes moving in the vertical direction, everyone? Is it moving in the vertical or horizontal direction? This moving vanes. Anyone would like to try? Can you see the vane moving in the horizontal or vertical direction?
Horizontal.
Okay, it is only horizontal. Can you see this imaginary line? Imaginary line focus on the horizontal position. That is why the VB is the blade or the vane in the horizontal position. That is why the power output directly related to the X component. We don't have in the Y component. So don't waste our time to derive for the Y component. So we need to derive 100% for the Fx, summation of force, equal to M, okay, V 2x minus V1x. That's it. Okay, so found by okay. We need to, since we have so many vein, number of vein, we have 1, 2, 3, 4, 5 vein. So we need to multiply this force by blade speed of each jet. Okay, so from here, in order to get the power output, this is the work dot. Okay, the work dot is referred to the power because it is the power, it is the work divided with time. This is symbol of dot referred to per time. It is the power. This is work divided with time, is the power, and reaction force, velocity. Okay, in order to get the total power of the turbine or from the vane, the number of vane, let's say it is 5, multiply with the reaction force in the X component, multiply with the velocity in the horizontal direction, which is VB, the blade velocity. The Y component does not move in the Y direction. Okay. So I think that's all for today. Thank you for your time. And tomorrow we're going to cover the propeller and dimensional analysis. That's it. Okay. So for the today recording video, I have posted in the e-learning. Please look at after this to revise on what we have learned so far. Okay. And as well as the tutorial for this chapter. I have made the tutorial for the propeller as well as for the deflector. Once you have a good understanding before joining the class, it will help you so much in understanding the subject matter.
Thank you, Doctor. Can you share the attendance code?
Okay, sure.
Doctor.
Yes.
For the last chapter of the energy equation, there were 2 questions. You said you will upload the tutorial, but you didn't.
Which one?
For the last, for the energy, for the last chapter.
Okay. Which one I didn't?
Yeah, you didn't upload the tutorial of the questions.
Okay. I think. Okay. Can you look at the tutorial in the e-learning? It is the tutorial
I checked,
video.
it was not there.
It is not there?
Yeah, because it's from week 8. You didn't upload tutorials after week. You didn't upload tutorial after week 5, I think, or week 6.
Have you looked at the e-learning just now?
Oh, not just now. I checked it like 2 days ago.
Okay, because today I already upload.
Oh, okay.
I already uploaded the new tutorial video for energy equation, for the deflector and propeller.
Okay. Okay, Doctor. Thank you.
Okay.
Doctor, I also have a question regarding the programming assignment.
Okay.
I finished everything. So just the last question about comments. So basically what we used to do with comments back in programming was like just to explain them the variables, because the naming is sometimes very different, or part of codes. Do we also need to explain how the code works?
No need. Just explain the complicated variable, how it
Okay.
works. Just
Oh,
two
yeah.
things. How it works, and then what is this variable? Because I need to understand your point of view.
Okay. Okay. All right. Yeah. Okay.
Okay,
Okay.
the assignment already extend into this. Okay, I hope that you manage to submit on time.
Well, it's expected when, Doctor?
On 19th of May before 5 p.m.
That's also another question. So, Doctor,
Okay, yes.
there is a part which says you have to snapshot your code.
Which one?
The Word document says I have to take pictures of my code.
Okay.
Doctor, I have 6